Hello, today I'm going to talk about the photoelectric effect and identify how it was first theorized that waves had particle-like properties. So, what is the photoelectric effect? The photoelectric effect is one of the three methods for, extracting electrons from a metal surface. And what happens here is by shining light upon a metal, we've got sodium metal here, or it's discovered that electrons are ejected from the surface. So that's what the photoelectric effect is. It's when looking at that in extreme detail came up some observations which led to the theorization of waves having particle-like properties. So let's look at that in a bit more detail. Milikan's experiment is the experiment which really captured the data which was then thought about and was used to develop some later thinking. And his experiment was very simple. So he accepted that incoming photons emitted photoelectrons. That seems fair enough. Now what he did is he made his target as an original sheet of matter, a photocathode, and then had a target which was an anode and had a voltage between these two metal plates. Now what this voltage did is what it allowed him to adjust the voltage, and by adjusting the voltage he noticed that he was able to stop the current, or photocurrent, which is the flow of electrons between the two plates. Now what he discovered that there was a certain voltage, what became known as the stopping voltage, of which no electrons were able to reach the target anode. Now, what this showed was that there was a maximum kinetic energy of these photoelectrons. The reason for that is because when an electron is released, its kinetic energy is going to be equal to the charge of an electron multiplied by the voltage. So therefore, this maximum point, this stopping voltage, is going to be related to the kinetic energy. So there we have the Milikan's experiment. Now, Milikan's experiment, he did a series of, extensions on this general experiment. And what he did is he investigated not just the voltage, but he also looked at changing the frequency of the incoming photons. So let me take you through some of the observations made and reveal some of the thinking behind explaining these observations. Observation 1. Okay. What he discovered was that if we look at this graph, we'll see that there's a certain frequency below which no electrons are emitted. So that's one thing, and this is the threshold frequency, and it must be met before photoelectrons are released. At the same time, if we increase the frequency past this threshold frequency, then the stopping potential becomes more and more. In fact, it's linearly related. So therefore we can see that by increasing the frequency, there's two things. The electron energy is dependent on the frequency of the instant of light, and there is a minimum frequency under which no electrons are emitted. So these are the two key things. Observation number 2 came about when he was looking at a comparison between the photocurrent and the voltage, and looking at this when having different intensities of light. So what we can see here, first of all, on the left hand side, we can see that there's a certain voltage where no electrons pass by, so there's no photocurrent at all. So that is equal to, that's the stopping voltage we spoke about beforehand. The key thing here is that stopping voltage is the same for every intensity of light. So the stopping voltage doesn't change because of the intensity. And furthermore, we can see that all the intensity does is it increases the number of photoelectrons, so increases the photocurrent, but not that kinetic energy, because kinetic energy is reflected by that stopping voltage. So here we can state that the intensity of incident light does not affect the energy of the emitted electrons. The third observation is that it was noticed that when incident photons were fired at a material, electrons were emitted instantaneously. Now this tells us that there's no time for a build-up of energy, no idea of the energy being pumped in by these photons of light until eventually reach enough energy to escape. The instantaneous means that there's no time for this build-up of energy. So these are the observations and the thoughts, and they were put together by Einstein. He put forward some hypothesis. He said that this means that light consists of quanta, which is packets of energy and momentum. The energy of one quantum is given by the formula E equals hf, where h is Planck's constant, 6.63 times 10 to the minus 34 joules per second, seconds, and f is the frequency. Now, these quanta of energy are called photons. So that means that one quanta, one packet of energy is called a photon. Now, how does this really explain what we've just seen? So let's put this into practice. A model used is known as the Electron Well model. So what we have is the electron is held within a potential well in the material. So that means when high energy violet quantum comes along, it provides energy to this electron. Now this electron must have enough energy to escape the well. Okay, and that we see in the green is known as the work function. And then beyond that, any additional energy goes to the kinetic energy of the electron after it's been ejected. So he's saying here that the quantum energy, which is Planck's constant times frequency, is going to be equal to the work function plus the kinetic energy. And this is normally shown as kinetic energy equals Planck's constant times frequency minus the work function. If we look at that graphical extraction earlier on, we recognize that there's a threshold frequency, and now if we think about the kinetic energy being plotted against the frequency, we accept the threshold frequency is there, but we'll notice that the gradient of the slope must be h, Planck's constant, and the negative intercept on the kinetic energy is going to be equal to the work function. So therefore, looking at this graph, we can extract some information. Think about a question now. A photo surface has a work function of 1.5 electron volts. Find the critical frequency. Okay, so first of all, we're finding the critical frequency. Try and answer that just with that information. Then furthermore, if the light of 6.1 times 10 to the 14 hertz falls on the surface, what is the energy and speed of the emitted electrons? Okay, so take a moment and try and solve those two problems. Then let me take you through how we'll do this. The first part of the question, the threshold frequency, well, if we know the work function is equal to Planck's constant multiplied by the threshold frequency, the critical frequency, so therefore the critical frequency is going to be 1.5 times 1.6 times 10 to the minus 19 divided by, and remember that's just converting electron volts into joules, divided by 6.63 times 10 to the minus 34 gives me a threshold frequency of 3.62 times 10 to the 14 hertz. Now the kinetic energy of the electron is given by the energy from the quanta of light minus the work function. So we've got 6.63 times 10 to the minus 34 times 6.1 times 10 to the 14, which we would have calculated, which can be calculated, which we're given, minus 1.5 times 1.6 times 10 to the minus 19, and that's going to be equal to 1.64 times 10 to the minus 19 joules. This can be calculated using half mv squared, so the velocity of this electron is going to be 6.0 times 10 to the 5 meters per second. So in review, we have to recognize that if light of a low frequency, so a longer wavelength, strikes, in this case, potassium, then there's not enough energy provided for the photoelectric effect to take place. If we decrease the wavelength and increase the frequency, therefore increase the energy being provided, then what we'll see is that electrons will be emitted, and if we keep on increasing the frequency, then what we see is that the kinetic energy of these electrons increases in turn. And that is my review of the photoelectric effect.